So in this lecture, we'll cover a new subtopic, which is the permutations of non-distinct objects, or we can also call it permutations of objects where all objects are not distinct. It's the same. Maybe the second definition is more precise because it says all objects are not distinct, some can be distinct. So let us consider a small example. Say we have to find 3-letter words from alphabets in all, right? So what do you see as a distinct difference from problems where what we have covered before? The two L's are same, so these are not distinct objects. You have A and L, so we don't have distinct objects, and we only covered permutations for distinct objects. So let us consider the case if they were distinct, and each L I will consider to be distinct and call it L1 and L2. So we know how to do this, right? So if we have this particular case, the 3-letter words are how many? Equal to 3 factorial, right? Again, I am just directly writing this 3p3 because there are 3 letters, 3 distinct letters, and you have 3-letter words. So it's 3 factorial. But what about if we had ALL? From ALL, we only have these arrangements: ALL, LAL, and LLA. So just 3. So why is that? And this is 6, right? So this is different from A. If all these 3 objects were different, you have 6, and otherwise you have 3. What is the difference now? Let us consider one particular arrangement. Let us see, I will just say LAL, for instance. So let us consider one arrangement like ALL, right? We have ALL. So if I had each of this L as distinct, like L1 and L2, corresponding to ALL, how many different words could I have? 2 factorial, actually. That is because you can have AL1, L2 and AL2, L1. These are different words now, right? If L1 and L2 are different. And why is it 2 factorial? Because you are arranging these 2 words, 2 objects which are distinct, taken 2 at a time, so it's 2p2 or 2 factorial. So you can arrange them in 2 factorial ways. So it will happen for each of these 3 cases, which is LAL. Here also you have L1A, L2 and L2A, L1, right? And the third one is LLA. Here also we have the same case, L1, L2A and L2, L1A. Okay, so each of this case, like these 3, result in 2 factorial more arrangements if L1 and L2 are distinct, right? So I will just see that the 3-letter words with all into 2 factorial are the 3-letter words with a L1 and L2. So when all these 3 objects are distinct, right? So the answer is basically that this is 6 factorial. Sorry. So this was 3 factorial, and you can divide it by 2 factorial. So this will be 3. As we saw from brute force, the answer is 3. So this is the basic idea behind permutations with non-distinct objects. So I will state a theorem. This was the intuition behind the theorem. So the theorem states that the number of permutations of n objects where p objects are of the same kind and rest are all different is n factorial divided by p factorial. So we won't prove this theorem, but like in the case of all, n is equal to 3, right? Because you have 3 objects and p objects are of the same kind. P is L here, like L is repeated 2 times. So here P is equal to 2. So the answer is basically n factorial divided by p factorial, which is 3 factorial by 2 factorial, and it's 3, like we saw before. So this is the theorem you have to remember. It's very easy. You just see how many objects you have which are similar to each other, and you divide the factorial, like p factorial. Let us consider a more difficult case where we have to form 9-letter words from the alphabets in institute. So do you think that the words are, like, if each alphabet is an object, are they distinct? No, right? Clearly you have I being repeated and T being repeated. So we have 9 objects with 4 distinct and 2 similar. 2 similar means that 2 of these objects are repeated. So 4 distinct, we just have N, S, U, and E as distinct objects, and 2 similar ones are I and T, right? I is repeated 2 times and T is repeated 3 times. So what would happen if all of these objects were distinct? For example, again, as before, I will call them I1 and I2, T2 and T3. So I'll just treat I and T as, each of these I and T's as distinct objects. Then we know how to solve it, right? Then we know that number of 9-letter words is 9 factorial, right? Again, that is 9p9, but I always keep on using factorial. So this is clear, but now because we have some objects which are non-distinct, 9 factorial will not be the answer for that. So we'll have to see, like for example, if I have one particular arrangement which is I N T S I T U E T. This is one particular arrangement, right? Which is fine, but how many such arrangements will be possible if I had I's as different objects and T's as different objects? So if each of these I's were different, then you could arrange them in 2 factorial ways, because there are 2 I's, like I1 and I2. And if you had all these T's as distinct, like T1, T2, and T3, then you can arrange them in 3 factorial ways. So for each of this particular arrangement of institute, we'll have more 2 factorial into 3 factorial ways. That is the number of ways in which you can arrange, say, I1 and I2 and also T1, T2, and T3, right? So they can be arranged in 3 factorial ways. I's can be arranged in 2 factorial ways. So you can arrange both of them together and get multiple instances of the same letter, same word, which will be different. So you have 2 factorial into 3 factorial instances. So similarly now, as before, I'll say that 9-letter words from institute into 3 factorial into 2 factorial is equal to 9 factorial, because that is the 9-letter words that can be formed with distinct objects, right? So I'll just say distinct objects, and I go down and see that the 9-letter words are equal to 9 factorial divided by 3 factorial and 2 factorial. So 9-letter words from institute, obviously. So that is when the eyes are not distinct. So this particular notion is like you just have to see how many of the words are similar to each other. So you have 3 factorial corresponding to the t's and 2 factorial corresponding to I, and 9 factorial is corresponding to the total number of objects. So this is a general theorem which I will state now. This is just the intuition behind the general theorem which I'll state now. So this is the general theorem where you have number of permutations of n objects, where p1 objects are of one kind, p2 objects are of second kind, and pk objects are of kth kind is n factorial divided by p1 factorial, p2 factorial, and pk factorial. So in the previous case where I had institute, I had 9 objects, so n factorial, so n is equal to 9 in that case. And how many objects are similar to each other? I and t, right? So I is repeated 2 times, so p1 is 2 and p2 is 3 because t is repeated 3 times. This is p1 corresponding to I and p2 is corresponding to t, and then the answer will be 9 factorial divided by 2 factorial and 3 factorial if we wanted to find the permutations like before. So this is the answer. This is a general theorem, so you can extend it even if you have p1, p2, p3 and so on. We won't prove it rigorously, but I just gave you an intuition, and we'll solve more problems about this and that will make it more clear.